Welcome to the session. My name is Michiel Bacchiani from Google, and I'll be telling you about Google research on end-to-end models for speech recognition. So first of all, I'd like to say that there's many people involved in this research work that I'll be telling you about. And so the people you see depicted here were my immediate collaborators, but there are many more people in the speech group. In fact, there's 240 more people in Google in the speech group. And furthermore, the speech research is very engaged with the academic community. So there's many conferences we attend, and there we meet other people from other companies and from universities. And that is an inspiration for this work as well. So that has pushed the field forward in aggregate. So with that said, I think I'll do a little bit of a recap of history. So Google started in earnest to do speech recognition in about 2005. And most people don't remember what it was in 2005. So let me recap a little bit what the world was like. So Google was very famous already. It was very popular. And the Google search engine was something that a lot of people used. But you only use this on your PC. There was no notion of mobile, anything like this. And the other thing that was popular is mobile phones. So they were everywhere as well. But mobile phones were not smartphones at that point. So they were really meant only to use for phone calls, not for the internet. Speech recognition existed as well as a technology, but mostly when you call the bank or something like this and you don't want to talk to you. So you'd say say 1 for sales, say 2 for service, things like this. So people really disliked speech recognition and didn't think it was useful. They just associated it with being annoyed when you call a company. So in 2005, when we started building speech recognition, one of the objectives was not just to build up the technology, but to sort of show people that speech recognition can be useful for you and it can be a good thing. So as I mentioned, a lot of people had cell phones, but if you're walking around and you wanted to call your favorite restaurant, you couldn't really do this unless you knew the number, right? And so frequently you don't know the number of the restaurant you want to go, you just know the name. So in the US, there's a phone number that is usually referred to as 411, where you can call and get some information. So what we did is we built a number called Google 411 you could call up. And then rather than talking to a person, you would talk to a speech recognizer. And you could actually ask for information. So you could ask the name of a restaurant, and then if we could find it on the web, then we would connect you. And that was the first time where people, I think, sort of saw that speech recognition can be useful because it can help you rather than being painful. Another thing we did is working on telephony. So a lot of people still use voice for a lot of things, and one of them is voicemail. And as you know, maybe if you get a voicemail, you want to just have the callback number, but people speak for a long time and then you just miss the number and then you have to replay it and so forth. So with speech recognition, we can actually transcribe the entire message, and then you have it like an email essentially, and then it's much easier to find the information. So again, speech recognition is a useful thing rather than something that is making your life harder. The third thing we worked on quite a bit is video captioning. So YouTube has lots of videos coming in, and we would run speech recognizers over the video to get automatic transcripts, so get subtitles and then particularly it's connected to translation, which gives a lot of people access to things you could never see. So if you have a Spanish video but you don't speak Spanish, but we run the Spanish speech recognizer on it and then you can translate it to English, suddenly you can look at the Spanish video even though you don't speak Spanish. So those are a bunch of applications that were nice and that actually made it somewhat interesting for people to use speech recognition, but it's nothing like we see today. So the big revolution, of course, was when the smartphones launched, and this was in about 2007. And that year, both the iPhone and the Android came out, and that really dramatically changed the status of speech recognition. And so suddenly people started really using this stuff a lot. And contrary to when they called the bank, people would voluntarily use it, right? So you have a smartphone, you can still use the keyboard. There's no problem doing that. But a lot of people decided to use speech recognition instead of the keyboard because they think it's more convenient. And this is now really taken off. So if you look at our services, we get several centuries of data. So every utterance is more or less 3 seconds. So if you think about how much traffic that is a lot of engagement from people. And we're launched in many, many languages, so we have more than 100 languages in production. So speech recognition now is a huge deal. So why is speech recognition so much better is what a lot of people ask, and usually get as answer, oh, it's artificial intelligence, which is somewhat true. But I'm going to continue with my perspective a bit, and I think explain that it's not so simple that it's just artificial intelligence. So a little bit of a simple overview, but an accurate overview of what speech recognition looks like is, you have your phone or your tablet or some other device, and you see that depicted there. And you would speak to it, and we would send that speech into the cloud, so into one of our data centers. And in that data center is some kind of process that's a speech recognizer that has a model and then tries to figure out what text goes along with your speech. And once we have the text, there are sort of several applications. So sometimes you really just want the text. So for example, if you want to send a SMS to somebody, what you want is the text, so you can send it to the person. But once in a while you want to do something with it. For example, you might want to do a web search, how old is Barack Obama? You don't really care about the string, how old is Barack Obama, you just want to get the answer. So after the speech recognition, we do a web search with that. And sometimes what we give back is not even text, it's for example speech itself. So if you're using a map and you want to say navigate to a particular location, you don't want text back because you might be driving. What you want is some speech saying turn right at the next traffic light and things like this. So it's quite complicated what's going on beside the speech recognition, but we'll focus here mostly on the speech recognition technology. So what is involved in a speech recognizer at a high level is fairly straightforward. Nothing has really changed from a very long time back. So there are sort of three components to a speech recognizer. One of them is the language model. And the language model sort of says, how likely is it that something is a correct sentence, right? So if you say, yeah, but, that is not very well-formed sentence, and maybe it's not so likely. If you say, I would like to walk to the store, or I would like to go home, that is in English a properly formed sentence, and therefore that has a high score. So a language model would give some kind of probability to any string you could say, but sort of making sure that things that are likely, that are a correct sentence, will get more probability than something that is an incorrect sentence. So the second component is a lexicon. So you have to figure out how to say something. So for sometimes it's quite simple. So if you have the word cat, you can sort of figure out that it's k, e, t. But there are complicated words as well, like through, which is very irregular. And then you have other problems there because on the web there's lots of new things for which you might not have a pronunciation. So we have systems called the letter to sound system, where you can give it any word and we'll try to guess what kind of phone sequence, what kind of sound sequence goes along with that word. And then the last component, which is the most complicated component, which is the acoustic model. So you get audio coming in, and that audio has to be matched to some kind of sequence of symbols, sequence of sounds, and then a particular word. And for that you need a particular model. And so if you look at our application, nothing is really particularly special here. So in the language model we need to do a little bit of special things. So for example, people use a lot of times or monetary amounts, and we would write them in a weird way, right? So you would say 7:15 a.m. or 7:15 in the morning, but we would write maybe 7:15 a.m. or $3.22. We would write in that way, not as a string. But other than that, there's nothing particularly special. We have some issues with pronunciation sometimes, so people frequently say URLs. So go red for women, it's written there as one URL. It's not so easy to figure out that that's what it's pronounced as. But other than that, it's fairly simple or straightforward and simple and analogous to what people have done before. So the new improvements don't come from a completely novel model here. But it is true that there is some component that has changed, and that is what people now call artificial intelligence, which is that people started using neural networks for the acoustic model of the speech recognizer, and that has made a big change. But the key issue is, you can see in the plot on the left, so you see the blue graph over there, which is the previous technology, and as you can see, if we get more and more data going along the x-axis to the right, you can see that the error rate, which is the y-axis, so lower is better. The error rate is coming down if we get more data, but it's going very slowly, right? So if we get a lot more data, we only get a small improvement. Whereas the black line, which is the new neural network stuff, or in 2010 new neural network stuff, you can see that we get quite a lot of gain by getting more data. The graph on the right is the results from a competitive evaluation. So there are many sites here that would compete in trying to get the best speech recognizer. So again, lower is better here. So the word error rate is along the y-axis. And at the x-axis you see the different years. So every year there'll be a competition where people try to build their best system and see who gets the lowest word error rate. And as you can see, in 2011 or so, there was a switch over from the what we used to use, a GMM, a Gaussian mixture model, to using a deep neural network for the acoustic model. And as you can see, the word error rate really came down at that point, and people really got much, much better at it. So looking a little bit more closely what was going on there, so this is the acoustic model at a high level. So you can see at the top left here, you have the waveform coming in. So that's the sound you speak into the microphone. And then what we do, we compute some features out of this. So at the bottom, that gray plot is what is called a spectrogram. And these are sort of the things that are derived from that audio waveform. And then on the right-hand side, you can sort of see the general layout of one of those models at that time. So that's what is called a deep neural network. So you have that spectrogram as input, that's the colorful input plane, and then there are sort of layered computations where weights would feed forward and would look at the previous layer and then compute whatever the output is, and that would go into the next layer and so forth. And so the main artificial intelligence that was used in those days is for the acoustic model. So you have the audio coming in, and at the output of that neural network, you would get some kind of probability saying this audio comes from a particular sound. So the probability of phoneme given audio. And so we worked quite a bit on this on other sites as well, doing all kinds of experiments. So how deep should that neural network be? How many weights should it have? What kind of connections should it have, etc., etc. So other things that we focused on is the objective. How do you train one of these things? And this is very similar to what we did with GMMs as well, but was hard to do with neural networks, but it's an important technology. And to get the idea of it is, let's say you have some utterance coming in, and let's say that the reference is somebody saying, okay, Google. And if you look at the bottom, maybe that's what the acoustic model would produce. So you get many of them right, all the green ones, but you can see there's two of them that it got wrong. So instead of okay, Google, it says, oh, hey, Dougal. Right? And so Dougal is not a word. And so once you connect it with the lexicon and it's searching, a lot of Dougal looks like Google, so probably the recognizer will still get it right, even though it has a d instead of a g. But if you look at the other error, you can see, it has an h instead of a k. So and hey is an actual word, right? So it might actually produce as a result, oh, hey, Google, which is not an insane utterance. So that dark red error is much more important than the pink error, even though they're both errors. You want to pay more attention to the ones where it actually screws up the result. And that is what is called discriminative training, and we make a lot of use of this. So the other thing that we and other sites started looking into quite early is the neural networks before, as an acoustic model, would only look at the sound, the current sound, and try to predict whatever the phone is. And then the next time step, we would have a new sound and we'd try to predict what the next phoneme would be. So we started using recurrent models, which is essentially the same network. As you can see, the A is replicated over time. But rather than just looking at the audio coming in, so X1, X2, X3, etc., we would also have some kind of state that feeds forward from the previous step. So we don't just do it as an experiment one by the other, but we have some kind of recurrency through time from which we can have better modeling. So as you can see, this made a huge difference. So if we use the old technology, the GMM, and for this particular task, you can see we're about 20% word error rate, and again, lower is better here. If we train this if we train these models, then with sequence training, we get quite a bit of gain. So we go down to about 16. But as you can see, once we started using the DNN, we got actually a much better result. Even the normally trained model would already beat the sequence trained GMM. And again, sequence training would still buy us an additional gain. And then the LSTM is the recurrent model, and you can see we gained even more. So that's sort of the current state. And if you now talk to Google or many other companies, you still talk to a model like this. This is sort of what is the state of the art that is in production at the moment. So as you noticed, contrary to the title of my presentation, I haven't started talking about end-to-end models yet. And I'm still not going to do that. I'm going to talk a little bit more in detail what it involves in building one of these traditional systems. So as I said, there's sort of three components to it. And the first one is the language model. So if you think of a language model, it's usually implemented like an n-gram. And so it's like a state machine. You can walk through the machine for any string that you have. So for example, if you have the top circle there, you might have seen as the last two words is a. And now you're trying to figure out what the next word is. So you might say is a man, or is a woman, or is a real something. And so to to implement the model, from that state you can take a transition. So is a man would lead you to a new state where maybe the new history is a man, right? Because you just transitioned from is a to a man. And that might have a probability of, say, 0.4 in this example. And so you can move through this machine and have a probability estimate for any string that you have. But of course, there might be many more words following is a. And therefore, you can also back off. So you have the epsilon transition, which is an empty transition, where you can forget a little bit. So then if you go down to the state below, the history is only a. And there you have many other words that you can omit, and so forth. So walking through this machine, you can get the probability for any string that is in the language. But if you think about how to design this, so the required things to design are a vocabulary, which are the words in the language that we allow. So you can't come up with new words. You have to figure out what the n-gram order is. In other words, any of these states, how many of the last couple of words do we remember? And then you have to figure out how to commute the probabilities and smooth them, how to estimate whatever the backup probability is. So that's the language model and the design that you need to do for that. Next, you have to come up with a pronunciation model. As I said, that's the second component to a model. And as you can see, you can still implement this as a state machine. So as you see the machine on the right, you can, from the start state, for example, see the word man, and then on the other side you can see n. So that's the pronunciation of man in terms of phonemes. And you can see on the left-hand side you emit words, so man and then empty and empty. On the right-hand side you have the phone, so n. And similarly you can have car and the walking in the other direction. So again, what does it require to build one of these things? Well, you have to figure out what kind of phonemes there are, so what kind of sound symbols do we have. Then you have to have some kind of pronunciation lexicon, so which words can you pronounce and what are they pronounced as. And then to come up with pronunciations for words you've never seen, you have to have some kind of letter to sound system. So that's all quite complicated as well. And as I said, finally there's the acoustic model, which now is generally a neural network, as I just mentioned. But there's a design as well, because generally we don't directly predict the probability of a phone, but we predict the probability of some state. So a phone sort of has the beginning and the middle of the end as an HMM depicted on the picture over there. And so the number of states is something you have to design, and you have to figure out what kind of neural network, how many neurons, etc., etc. So there's quite a bit of design into one of these systems that we use today. And then finally there's the overall system. So as I said, when your speech comes into the data center, you have some kind of recognizer that you would use to try to figure out what it is that's being said. And it has to combine all of these models, right? There's the language model, the pronunciation model, and the acoustic model, and it has to perform some kind of search to figure out what it is that the word sequence is. So there's a lot of design and a lot of engineering involved in getting one of these speech recognizers to work nowadays. You have a recognizer, you have the design of all these models, you have to train all these models, so it's quite involved to build one of these systems. So here we get to sort of, what the more modern end-to-end systems are. And so the end-to-end systems are called sequence-to-sequence. And the general outline of these models are depicted on the right. So again, you have the audio coming in, and you have the text coming out at the top there. And these models are what is called encoder-decoder models. So the audio comes in, and it has a bunch of neural layers, generally CNNs or LSTMs, that come up eventually with what is called an encoder source. So you have some kind of representation of the audio after it's been transformed by the encoder. And then there's an attention mechanism and a decoder. And so the decoder will produce output symbols and will pay attention to the audio to figure out what the next symbol should be. So it sort of looks at the audio in that representation to figure out what the next symbol to output is. So the decoder is usually an LSTM. It could be somewhere else, and it has things like embedding in a softmax. But it's still sort of a fairly straightforward neural network. The thing that is interesting is the attention mechanism, which is sort of aligning the output of the symbols with the audio coming in. And so these are remarkably interesting models. And so why are they so interesting? First of all, there's no more separate models, and there's no more independence assumptions. So as you can see at the top, the probability of the next output symbol is dependent on all the previous symbols. So there's no more n-gram approximation, and it's dependent on all of the audio. So there's no independence assumptions, no separate models. It's a full distribution. The other thing that's interesting, there's no more separate models, so everything is jointly optimized. If you train these things, you train the entire model. You're not building separately the language model and then separately the acoustic model and then separately the pronunciation model. It's one model, which is very compact and very well optimized because everything is optimized together. And very importantly, there's hardly any design here, right? The audio comes in, you have to figure out what the neural network looks like, and symbols come out. And there's no definition of phones, there's no definition of vocabulary, there's no n-gram order, etc., etc. So there's a lot of research now on these models, and there's lots of different flavors of these models. So there's listen, attend, spell, there are transformers, there are now new conformers, there's all kinds of models. But essentially they're all the same flavor here, where they're end-to-end. So audio comes in, text comes out, there's no understanding what's in between, it's just a neural network. However, there's lots of issues that come up when using these models, right? It sounds really, really great, and it is actually great, but lots of things that we could do in the old world are sort of hard to do in the new world. So for example, for the old models, we have a lot of text. There's, for example, the web, but we don't have the audio that comes with the text. But the text is itself very useful because it gives us a good idea on how to build a language model. And since the end-to-end models are end-to-end, they can only learn from actual paired data. Only if you have the audio and the text can you actually learn something from that data. And so how do you make use of a language model is not obvious. So people have tried various things called fusion. So you would have a language model that you would run in parallel with everything else. And so rather than having the softmax just output whatever the next symbol is, you would also use the language model to influence this. And so if you have the language model cost and the softmax cost together, it's called frequently called shallow fusion. Or the other thing you can do is you can have the decoder pay attention to the language model state, which is called deep fusion. So for shallow fusion, you have some results here on the left. So the baseline here is, you see def and test set, and these are word error rates. So again, smaller is better. And as you can see, if you have just the end-to-end system, listen, attend, spell system, you get a particular error rate. If you do shallow fusion with a language model or with a large language model, you can see we get quite nice gains. And even if you use a more complicated language model like an RNN, you get even larger gains. So this is a way to incorporate the language model, but it's not obvious how to do this because it's not paired data. And it's not obvious on how to put this in an end-to-end system. Another thing that's very important to us is that we want to do online processing. So if you think about it, if you speak to Google, you don't want to Google to start processing your speech when you're done talking. If you talk for 10 seconds and you have to wait another 10 seconds before you see the answer, you would be very unhappy, right? You'd like us to get started doing speech recognition as soon as the audio comes in, not later. So the end-to-end models, though, as you can see, are conditioned on all of the audio. So you would have to wait until the end to actually do the full model. So what we do is we actually chop this up in pieces, into blocks, and then we have the end-to-end model sometimes predict that it wants to move to the next block, and then we can do online processing like this. And so if you initially do this, you get somewhat of a degradation. So the word error rate used to be 11.7 and degrades to 14.6 if we do this. But if we pre-train this and do some training tricks, we actually can get rid of most of the loss, if not all of the loss. So again, this is a lot of engineering to make something work that was previously easy, but now is somewhat complicated. A third thing we like to do is if you, for example, call one of your friends, and your friend's name is probably in your contact list. So what we do is we add, at the last moment, the name of your friend to our vocabulary, to the lexicon, and we make it more likely in the language model, which is called biasing. So in many cases, biasing comes up, right? So for example, if you talk to YouTube and you want to ask for a song, we know what songs exist, and we want to make sure that it comes up with that and not with something else. If you talk, if you want to dial your phone to somebody, that's called contacts. We know which contacts you probably want to use. So again, in the old system, it's quite easy to splice it into the lexicon because we know where the lexicon is and we know where the language model is. For these new models, it's not obvious on how to do this. So we come up with something that's called CLAS, conditioned listen, attend, spell. And as you can see, the model structure is on the right. So it's still an encoder-decoder model. So the audio comes in on the left and we do attention in the decoder. But the decoder, in addition, can pay attention to something else, which is the biasing. So in the biasing, we feed those contact names or song names into an encoder, and then the decoder can pay attention to those as well. And as you can see, if you don't do this, you can get quite high error rates on these tasks, but as you can see, if we do this biasing like this, we can recover a lot of that error. So in summary, these end-to-end models are of great interest. They're very compact, they're very easy to build because there's much less design. And they have no independence assumption, so there's lots of positive things to them. However, they're very hard to interpret, right? We don't know anymore where the lexicon is, we don't know anymore where the language model is, etc. And therefore, doing some things that we used to do quite easily are made more complicated. So that's why there's still a lot of research going on into end-to-end models for speech recognition. But they remain interesting, and I'll do a little bit of advertisement here. So I started a new speech group here in Tokyo, which is focused on doing end-to-end research, not just for speech recognition, but for more stuff. And so these are sort of the people that are currently in the group. And so some of them have transferred from other places in Google, some of them are newly hired from the outside, some of them are quite junior, some of them quite senior. And it's sort of a mix of people that are focused on speech and language processing. So a very good example is related to Japanese. And I think maybe a lot of the audience here is Japanese, so maybe this is a bit boring, but let me make sure that I cover everybody. So if you think of Japanese, there's 4 kinds of scripts that are used. So Romanji is used mostly for acronyms like DVD, katakana for loan words, so computer would be written like this, and then hiragana and kanji are used for most of the other stuff, and there's some kind of duality between them. Konnichiwa is written there in hiragana, could also be written in kanji on the right. So for Romanji, katakana, and hiragana, the pronunciation is quite simple, in the sense that it's easy to figure out what the sound should be. However, for kanji, this is quite complicated. So for example, the kuruma character you see on the right, which means car, would have at least 2 readings, the kunyomi and the onyomi, and it could either be kuruma or sha. And depending on where it's used, for example, if it's just a car, it might be a kuruma. If it's a rosha, a train car, it might be pronounced as sha, which depends entirely on the context. And if you look at something like hi or nichi on the right, you can see there's many different reading forms as onyomi and kunyomi. And the example sentence at the bottom, which isn't that complicated, March 1st was a Sunday, it was a national holiday, and it was a sunny day, is not a very complicated sentence, but as you can see, there's 5 occurrences of the day symbol, and they're all pronounced differently. Tsuitachi for the first of the month, Nichiobi as Sunday, etc., etc. So it's very hard for a speech recognition system to predict, if you see that string, what the pronunciation should be. It's very hard to figure it out unless you somehow come up with the right pronunciations for each of the characters. So, and this is particularly bad for the kind of technology that we have, because as I explained in the baseline system, a lot of it is based on tokens, right? You have words and you transition from one word to the next. You have phones. They're all sequences of symbols. But for CJK, so Chinese, Japanese, or Korean, it's not such a natural choice, because there's no notion of a word. There's no spaces in Japanese, as a lot of people would say. And so it's very hard to deal with this, because we have to somehow make it work with the technology that we have. And so the way that people do this is by introducing a segmenter early on in the process, which tries to chop up the Japanese into something that is like words. And so the most commonly used technology for this is what's called Mecab, and this is invented by somebody that's now in the Tokyo office in 2004, and it basically would do an analysis as written over there. So the sentence here is Tokyo to Nisumu, and which means I live in the metropolis of Tokyo, but you could segment this in many different ways. And if you would segment it in the wrong way, as you can see in the letters representation underneath, the reading might be completely different, right? So if you just have the east symbol, it might have kunyomi, and it becomes higashi, rather than to in terms of Tokyo. And so you can, this technology uses a conditional random field to estimate whatever is the best path through this lattice, what is the best way of segmenting it. And then, associated with it, you would have decent pronunciations for each of the morphs. But if you make a mistake, and for example, if you take the basic Mecab installation and pass that sentence through that I just showed you, it already makes a mistake. Rather than doing tsuitachi by noticing that it's the first of the month, it separated one and day, and then it becomes ichinichi, which is completely wrong. The other thing that's a problem here that is very similar to speech recognition is that it's sort of state of the art, but as you can see, there's lots and lots of resources. So here are the file listing of the standard implementation, the standard installation, and you can see there's lots of lists of nouns and adverbs, etc., etc. So there's a lot of design, just like in the speech recognition system, where we had the phone set and the vocabulary and so forth. So this is doubly bad in the sense that you have an early decision that you have to make, which makes mistakes, and you have a lot of design to make that happen. So again, here the end-to-end models are actually quite interesting because we don't have to do this anymore. So in this experiment, what I did is we use Japanese speech, and then using Mecab and our production ASR model, we can figure out how a particular written string is pronounced as phones. And then we can train encoder-decoder end-to-end models to see if we can predict from one string to the next. For example, here S to P is from speech to phoneme, P to G is from phoneme to grapheme, etc., etc. And as you can see, going from speech to grapheme is quite complicated. So predicting whatever kana or kanji or other script comes out. But as you can see, it's also, you can go from speech to phone and then phone to grapheme, which is slightly better than going from speech to grapheme. It's already non-additive in terms of the error rate. So the other interesting thing you can do is you can now do multitask end-to-end models, right? So you can have the input signal, the speech coming in, going through the encoder just like before, and then you could have multiple decoders looking at the encoder, for example, to predict both phonemes and graphemes. But something to realize is that these decoders are still independent, right? They don't see each other, and that's sort of suboptimal. So what we did is we extended this to something that is called refinement. So if you look in the middle of this graph, you still have the audio coming in, and you have an encoder just like before, and then you have the two decoders on top of it that try to predict phonemes or graphemes. But once you have the output of this, you can have it input in another block. So you have another encoder on the left and another encoder on the right, which re-encodes the previous state's phoneme result or grapheme result. And then the decoders can look at all of these encoders to figure out what the next result should be. So if you look at the error rates there, if you just go from speech to phoneme, we get 8.8%. If you go from speech to grapheme, you get the error rate over there. And then if you do a multitask, what I just showed at the previous graph, you can actually get somewhat of an improvement by doing this. But as you can see, the refinement further improves it. So the model benefits from seeing the grapheme can be a better prediction if it also knows what the phonemes are predicted and vice versa. So how can we generalize this even further? Like I said, there's a new research group here, and what we're looking at is that you can go beyond this modeling and say can you do more with the encoder-decoder architectures? So not just predict speech recognition and get the text out, but can you model other things like natural language processing? And this is beneficial for many things. So first of all, it might remove a lot of the manual design. So like I said, the Mecab thing has tons and tons of design. The speech recognition system has tons and tons of design, which you can all get rid of. And this joint optimization is beneficial. Like we saw with the grapheme phoneme prediction, predicting it jointly is a much better idea than trying to do it separately. So generalizing this further, you could have something that is a structure that we're looking at quite a bit, where you would have an encoder encoding the speech. And we don't just envision doing a grapheme decoder output, which would be a traditional ASR task, but in addition we can do phone prediction, part of speech prediction, etc., etc. So we can do many more natural language processing jointly. And if we jointly model this, we might actually have a benefit. So in other words, a particular sentence has to be grammatical, and if the part of speech sequence says it's all verbs, it's very unlikely that that's correct transcript. So they can enforce each other and be consistent to get a better, more accurate output. Something else we have learned though, and that is a current avenue of research, is that for BERT modeling, where we do language model and for traditional NLP, the encoder is considered to be very important. And something we learned from BERT is that if the encoder is well trained, unsupervised, and learns about language, the upstream tasks are much easier to do. So we're looking at this for audio, and so something that's been an active field of research is what is called CPC, contrastive predictive coding, and there's many other follow-up research on this coming out, where we basically take the audio coming in and we try to find a model that encodes most of the audio that is not surprising. So the structure that is inherent to the audio we can try to find, and then if we do predictions on top of that, it's a lot easier. So this is also called representation learning, and something that is now very actively in production. So this is, trying to find a better encoder, or a unsupervisedly trained encoder that represents the speech very well, and then we can do those many tasks on top of it. So in summary, what have I told you? So speech recognition has really transformed from 2005 to now to be a much more accepted technology. So before people hated it, now people find it very useful, and it has a lot of engagement. It is true that artificial intelligence has played a role in this, but I hope that I stressed out that it's more the user engagement and the user acceptance of the technology that has given us a lot more data. That is a very essential thing for speech recognition to improve. Neural modeling has also expanded. So previously it was only used for the acoustic model, which really pushed the performance up. But novel models are what is called end-to-end, and is an avenue that keeps receiving a lot of attention, just because it's so attractive in terms of design, in terms of the compactness of the model, and how to do better modeling with it. And the sort of way of the future, we do a lot of novel research trying to do ASR jointly with NLP as one end-to-end model, again for accuracy as well as for simplicity of design. So thank you for your attention. I hope that this is an interesting presentation, and I thank you for your attention.